Hello everyone, how are you? I hope you are all doing well. So, my name is Vinod Kumar and in today's lecture we are going to study the electric field due to a uniformly charged thin spherical cell. Okay, so let us assume that there is a thin spherical cell of radius capital R. There is a thin spherical cell of radius capital R, and let us suppose that it is uniformly charged. Okay, let us suppose that it is uniformly charged and the charge density, the surface charge density of this spherical cell is sigma, and the unit of this surface charge density is coulomb per meter square. Okay, so now we are going to study the electric field due to this spherical cell, where the sigma charge density, that is, we can say the charge is uniformly distributed over the surface of this spherical cell, and it is in spherical cell. And now the first case which we can study is, we can say that field outside the cell. The field outside the cell, that means we can say that we have to take some distance r greater than capital R, where capital R is the radius of this spherical cell. Let us assume a Gaussian spherical surface such that its radius is small r, and where small r is greater than capital R. That means the Gaussian surface, or we can say the Gaussian spherical surface which we are taking out, that is bigger than the spherical cell which we are taking. And both we can say this outer Gaussian surface and the spherical cell, both are concentric. That means they have the common center at O. Okay. Now, if the surface charge density is sigma, then we have, first of all, we should know that what is the charge enclosed by this Gaussian surface, the outer Gaussian surface which we have assumed. So it will be Q enclosed equals to sigma into, since we know that the charge is uniformly distributed over the spherical cell only. So the total charge which is included, or we can say enclosed in this outer Gaussian surface, that will be due to this spherical cell only. That means the charge density into its area. And if the radius is r, then the surface area of the spherical cell will be 4 pi r square. This is the charge enclosed in this outer Gaussian surface which we have taken. Okay, now according to Gauss law, the electric flux, that means the electric flux passing through this outer Gaussian surface, that will be written as closed integral over E vector dot ds vector equals to Q enclosed by epsilon naught, where epsilon naught is the permittivity of free space and Q enclosed is the charge enclosed in this outer Gaussian surface. We can say inside the outer Gaussian surface what is the charge enclosed. Okay, now this closed integral means whatever is it is a closed circle. As we know that the requirement of Gaussian surface is it should be a closed surface. So that is why the closed integral is taken here. Now, as we know that if there is a positive charge accumulated here on the thin spherical cell, then as we know that positive charge, the field due to positive charge is normally outwards. Fine. And now the area vector due to this outer Gaussian surface, that will also be normally outwards. That means the direction of electric field and the direction of area vector both are same for this given case. Now, so it can be written as, and as we know that the electric field, whatever points we are taking here, let us say we can take a point here, anything, anywhere on this circumference of this, we can say spherical Gaussian surface. It is same because the distance is same. That will be small r only. So that is why the electric field is same at each point. So that is why we are taking it outside. And ds equals to, the q enclosed is sigma into 4 pi r square upon epsilon naught. Sigma into 4 pi r square into divided by epsilon naught. Now, what is the surface area? What is the surface area of this assumed Gaussian surface? It is 4 pi r square. So that is why it can be written as E into 4 pi small r square equals to sigma into sigma 4 pi capital R square by epsilon naught. Now this 4 pi and 4 pi will cancel out and we get the electric field as E equals to sigma capital R square upon epsilon naught R square. This is the electric field due to this Gaussian spherical, this is the electric field due to uniformly charged thin spherical cell at the outer point, or we can say outside the cell, where sigma is the charge density. Okay. Now, if we convert this charge density in terms of charge, let us say if the total charge is Q, if the total charge is Q, then it can be written as sigma can be written as Q by 4 pi r square. It can be written as Q by 4 pi r square. So let us place this in this equation. We will get E equals to Q into R square divided by epsilon naught R square into 4 pi R square, and finally we will get the equation as Q upon 4 pi epsilon naught R square. 4 pi epsilon naught R square, this is the electric field. This is the electric field outside the spherical cell, where Q is the total charge on this spherical cell. Now, if we want to write in the vector form, then it can be written as in vector form it can be written as E vector R equivalent to Q upon 4 pi epsilon naught R square into R cap, where R cap is the direction radially outward. Okay, this is the electric field due to if the positive charge is uniformly distributed over the spherical cell, and it is normally outwards. And if there will be a negative charge, then the direction will be inwards. That means it will be normally inwards towards the radial direction. Okay, that's what the electric field outside the cell. Outside the cell. This is the electric field. And as you can see that it is the same field which we get due to a point charge. So that is why we can say that we can conclude here that the electric field due to a spherical cell is such that the charge is, we can say it is accumulated at its center point. It looks like that only. So we can similarize both the cases, due to a point, the electric field due to a point charge and electric field due to a spherical cell. Okay. And we can see the dependency, that is the electric field outside the cell. It is 1 by proportional to 1 by r square. Proportional to 1 by r square. Okay. Now the second case we can include in this only, that at r equals to r. At r equals to r, the electric field will be q upon 4 pi epsilon naught r square. This will be the electric field at the we can say the distance equivalent to radius of the spherical cell. Now the third case which we are taking here, third case, the field inside the cell. Now the third case which will take field inside the cell, and in this case the radius of the Gaussian surface which we are going to assume, it should be less than the radius of the spherical cell which is given. Okay. So this time the outer surface we are not going to take. We are going to make a Gaussian spherical surface inside the spherical cell. So let us assume that there is a spherical Gaussian surface such that its radius is less than the radius of the spherical cell on which the charge is placed, or we can say that it is uniformly charged. Now this time, according to Gauss law, okay. Now if you want to find out the charge enclosed due to this spherical, the spherical Gaussian surface which is inside the spherical cell, it is, we know that all the charge is distributed on the surface of the spherical cell. No charge is there inside the spherical cell. So that is why we can say that it is zero charge inside the cell. Inside the spherical, no charge inside the spherical cell. So there is no charge inside the spherical cell. So that is why we are, if we write in the Gaussian law, we can say the Gaussian law. So it will be E vector dot ds vector equals to q enclosed upon epsilon naught. So the electric field again it is same at all the points, so it can be taken out, and the area which we are going to take is this time, it will be due to this inner Gaussian surface. So it is 4 pi r square equivalent to q enclosed is 0, so 0 for epsilon naught. So that is why we can say that. That is why we can say that the electric field inside a uniformly charged spherical cell is 0. So here we have studied three cases. And if we note down them, so it can be written as, this is the case inside the spherical cell. Now the second case which we are going to take, it is on the, we can say the distance equivalent to the radius of the, at r equals to r. And the third case, now this time the radius of the outer cell will be r greater than capital R. And now the electric field we want to write, that will be E equivalent to 0 for this case, and E equals to q upon 4 pi epsilon naught r square, and for this case it will be And if you want to write in the vector form, then it will be like that. So E vector equals to Q upon 4 pi epsilon naught R square into R cap. This will be the electric field